All right, we're going to be working on Math 1 Honors 9.3 task. So we're going to be working with some quadratics again. So we'll start with this first problem. What happens when you drop a ball? It falls to the ground. That question sounds as silly as why did the chicken cross the road? Seriously, it took scientists until the 16th and 17th centuries to fully understand the physics and mathematics of falling bodies. We now know that gravity acts on the object that is falling in a way that causes it to accelerate as it falls. That means that if there is no air resistance, it falls faster and faster, covering more distance each second as it falls. If you could slow the process down so that you could see the position of the object as it falls, it would look something like this picture. So to be more precise, objects fall at a constant rate of acceleration on Earth of about 32 feet per second per second. The simplest case occurs when the object fall starts from rest, that is when its speed when t equals 0, like here, t equals 0. In this case, the object's instantaneous speed after 1 second is 32 feet per second. So if this were like t equals 1. After 2 seconds, its instantaneous speed is 2 times 32 because it's falling faster now. So at like t equals 2, it's going 64 feet per second and so on. Like t equals 3, 4, 5. So if the acceleration, other planets and moons have the different rate of acceleration, but the basic principle remains the same. If the acceleration on a particular planet is g, then the object's instantaneous speed after 1 second is g units per second. After 2 seconds, it's 2g, and so on. So in this task, we will explore the mathematics of falling objects, but before we start thinking about falling objects, we need to begin with a little work on the relationship between speed, time, and distance. So consider a car that's traveling at a steady rate of 30 feet per second. And at time 0, the driver of the car starts to increase his speed or accelerate in order to pass a slow-moving vehicle. The speed increases at a constant rate so that 20 seconds later, the car is traveling at a rate of 40 feet per second. So thinking about, distance equals rate times time, rate being speed. Okay, you have graph the car's instantaneous speed as a function of time for this 20-second time interval. Okay, so when we started talking about it's going to accelerate, it was going It was going 30 feet per second. And then it says the speed increases at a constant rate so that 20 seconds later, okay, time in seconds is here, so 20 seconds later here, the car is traveling at a rate of 40 feet per second. So 20, 40 here. Okay, so the average on the interval from 0 to 20, in this interval from 0 seconds to 20 seconds, we're going to talk about this on the next page, and then we'll come back to this graph. So it says calculate the average speed of the car for this 20-second time interval. So you're going to look at the endpoints of the interval. So those endpoints are 0, 30, and 20, 40. Okay, so if you have the speed 30 and speed 40, then if you want the average, then wouldn't you just add them and divide by 2? So you have the average on that interval from 0 to 20 seconds is 35 feet per second. Then it says find the total distance the car travels during this 20-second time interval. Well, you know that rate times time equals distance. And so if you know their average rate, which was 35, and you know the time, which is 20 seconds, then you know their distance. So finding the total distance would be 700 feet in 20 seconds. So now it says explain how to use area. It's talking about area represented on that graph. Explain how to use area to find the total distance the car travels during this 20-second interval. So if I'm going to use our area, I need to go back to this graph where I right now only have 2 points. And I'm going to actually connect the endpoints to make an area. So go ahead and graph down here to actually make a polygon that I can figure out the area. Okay, so when you connect all the endpoints, you can see that this is a trapezoid. And if you want to figure out the area of a trapezoid is B1 plus B2, base 1 plus base 2 over 2 times height. Okay, now this trapezoid, in essence, this would have to be the height because the height has to be perpendicular to the base. And then I call this B1, which in this case is 30, and base 2, which in this case is 40. And then I can figure out the area of this trapezoid. So I have 30 plus 40 over 2 times 20, area of this trapezoid. And I have area equals 35, right, times 20, which is 700. So if you notice, what we got when we used the average rate and the time to find the distance, it was 700 feet in 20 seconds. And now, since it says explain how to use area to find the total distance the car travels, then you could sort of recreate the situation. You have this trapezoid, right, where this is 30, this is 40, this is 20. And you have 30 plus 40, the area of a trapezoid, divided by 2, times height, which is 20, which is 700 feet. So now it says explain how to use the area. So the explanation is the area between the line, like this line that we graphed, and the x-axis on an interval 0 to 20 is distance traveled. Okay, so you can use the area under that graph to show the same thing that we found in the other method. So this problem illustrates an important principle. If an object is traveling with constant acceleration, then its average speed over any time interval is the average of its beginning speed and its final speed during that time interval. So let's apply this idea to a penny that's dropped from the top of the Empire State Building. The initial speed is 0 when t equals 0, meaning it's falling from a still place. It's not being thrown or with force. Just dropped. Be sure to reference the second paragraph at the start of the task for information about the constant rate of acceleration. So what will its instantaneous speed be after 1 second? Well, if you go back here, it actually says on Earth, the object's instantaneous speed after 1 second is 32 feet per second. So that's the same pennies or whatever it was that we were talking about. So 32 feet per second, and this is from the introduction paragraph. You can get that information. So complete the table of values for the penny's instantaneous speed over time. Then graph the penny's speed as a function of time in 1 second intervals. Okay, so we have 0, well, then it's going 0, 1 second, 32, 2 seconds, 64, 3 seconds, 96. 4 seconds, 128, 5 seconds, 160, and then go ahead and graph it. So you have 0, 0, you have 1, 32. I mean, you really don't have to graph them all. You just need to go from 0, 0 to 5, 160, because you know it's going to be a straight line. So, go ahead and use my straight edge again. All right, so we have that graph. It says, what is the average speed of the penny in the 1 second interval? Well, same thing. We have an interval. The interval is 0 to 1, right? That's the 1 second interval. So, these endpoints are 0, 0, and from 0 to 1 on that interval, the endpoints are 0, 0, and 132 in that graph that we just graphed. So I'm just going to take the average. 0 plus 32 over 2 equals 16 feet per second. So now what is the total distance that the penny fell in the 1 second interval? Same thing. We have average speed, which is 16, times time, 1 second, equals distance, 16 feet, just like we did before. All right, so complete the table below for the speeds and distances traveled of a penny dropped from the top of the Empire State Building. Okay, now think about these headings here. You have time. Time is in seconds, so I'm just going to put that, seconds. Instantaneous speed is in feet per second. Average speed is always on the interval, just like we did up here, number 7. Average speed is on the interval from 0 to whatever time you're talking about, 0t I'll put. And then distance traveled, you'll find is the same, right? This is on the interval. Distance traveled on an interval from 0 to t. Because this is like you're going to figure this out because you're going to have the average speed times the time. Okay, so let's go ahead and fill this in. So time in seconds, you have 0, 1, 2, 3, 4, 5, 6. Okay. Instantaneous speed, you have 0 feet per second, then 32, 64, 96, 128, 160, 192, right? Because you just keep adding 32 to that. But then this is the part you really need to think about. You want the average from, what's the average from on the interval 0 to 0? Well, it's 0, so it's traveled distance 0. But what's the average on interval 0 to 1? So I want the speed at 0, the speed at 1, and the average of that. So that's 16. And then on the interval 0 to 2. So that's 0 to the speed at 2, 64, divided by 2 is 32, and so forth. You can see that this is going to keep happening. On the interval from 0 to 3 seconds, it's 0 plus 96 divided by 2, 48, and then you see it just keeps being half of this. But you need to understand why, so that when we do another one later, it'll make sense why it's not always a half, but in this situation. Okay, distance traveled is average speed times time. So average speed times time, 16 times 1, 16. 32 times 2, 64. 48 times 3, right? Because average speed times the time that we're talking about is 144. 64 times time 4 is 256. And then 80 times 5, which is 400. And then 96 times 6, which is 576. Okay, so we've completed the table for what we have so far. So the Empire State Building is 1,250 feet tall. Approximately how long will it take for the penny to hit the ground? Well, we could use the area of the triangle from the penny graph. So we could go back to the penny graph, so here, make a triangle, and figure out the area. Right, that worked with our car. Okay, so here's my triangle, and area of a triangle is 1/2 base times height. So I already know the distance. I mean, 1250 is the distance that I'm traveling because it says it's going to go from the top, which is 1250, all the way to the ground. So I already know the distance. And distance is the area of the triangle, right? Okay, so let's just set up a with area equals 1/2 base times height, we can set up a formula. So I know the area, 1250 equals 1/2. And then what's the base? Well, the base here is 5, but did it take 5 seconds? I mean, at 5 seconds, did it go all the way? No, but I do know that however long it took, it's time. So I'm just going to use t for my base. T is time. T equals time. And then I know that the height is 32t, because I know that that's how fast it's traveling. So 32t. So I need to solve for time. It says how long. So how long is time? So I have 1250 equals, well, 1/2 times 32t times t is 16t squared. And I can go ahead and divide by 16. And I get about 78.125 equals t squared. And then I want to figure out about how long. So I want t, I don't want t squared. So I'm going to take square root of both sides. And t ends up being about 8.84. So I'm going to say that actually it takes between, I'll just say it takes between 8 and 9 seconds. So if I continued my table up here and kept going with 7 seconds, 8 seconds, 9 seconds, you would see that it actually, this number out here would end up between these two numbers, between 8 and 9, would end up a number for 8 seconds would be a number lower than this, and for 9 seconds would be a number higher than this. But I don't want to have to always finish my table like that. It would just take so long. So it's just easier to use algebra. All right, let's look at another situation like this. So now, falling from the moon is a little bit different. So when the astronauts went to the moon, they performed Galileo's experiment to test the idea that any two objects, no matter what their mass was, will fall at the same rate if there's no air resistance. So because the moon doesn't have air resistance, we're going to pretend like we're astronauts dropping moon rocks and thinking about what happens. So on the surface of the moon, the constant acceleration increases the speed of a falling object by 6 feet per second per second. That's different than Earth, what we were talking about before. So that is, if an object is dropped near the surface of the moon, its initial speed, 0, when t equals 0, then the object's instantaneous speed after 1 second is 6 feet per second. After 2 seconds, its instantaneous speed is 12 seconds per second, and so on. So using the information, complete the table below for the speeds and distances traveled of an object that is dropped from a height of 200 feet above the surface of the moon as a function of the elapsed time in seconds that it was dropped. Okay, so you have seconds right here, right? And then you have instantaneous speed, which is feet per second, and then average speed, which is, remember, on the interval from 0 to t, remember? And then this distance is also in the interval 0 to t. All right, so we'll start with 0. So I have 0, 1, 2, 3, 4, and then I'm going to eventually want to figure out what at any time is. So instantaneous speed at 0 is 0, 0, 0. Okay. Instantaneous speed at 1 second, it tells us above here, is 6. And at 2, 12. And at 3, 18. And at 4, 24. So what's happening with this rate? It's just adding 6 every time. And then you have average speed on the interval from 0 to whatever second you're talking about. So the average speed on the interval from 0 to 1 is like the average. 0 plus 6 divided by 2 is 3. And then 0 to 2 is 6. And 0 to 3 is 9. And 0 to 4 is 12. Okay, and then over here, remember this is distance traveled. It is average speed times time. So time 1 times average speed 3 time 2 times average speed 6 times average speed is distance. And then write an equation for the distance the object has fallen as a function of elapsed time, t. Well, I had put this t down here to figure out if I have t and I multiply it times the average speed, what keeps happening with all of these? Like, if I want to find the distance, I notice that it's whatever the time is times 3 times t. So I have actually 3. So I have time times the interval times 3. Because that's how I always end up with, I get this by multiplying it by the time. So I have time times 3. So my distance in terms of time is 3t squared. And it says, approximately how long will it take for the object to hit the surface of the moon? Well, up here it says that it's 200 feet above. So I know the distance, 200. I'm going to use this equation. Distance equals 3t squared. And go ahead and solve it. So I'm going to divide both sides by 3. And I get t squared is about 66.6. So that means when I take the square root of both sides, I get t is about 8.16. So about 8.16 seconds is how long it'll take. So write an equation for the height of the object above the surface of the moon as a function of elapsed time, t. Reminder, the object is dropped from a height of 200 feet above the surface of the moon. So you might be thinking, oh, we already wrote an equation. Well, this is the equation for the distance it's traveled. But this is an equation for the height. So I really want h of t. What's the height of at any given time? So if I want the height at any given time, then I take the total height, right? This is the maximum height, and subtract the distance that is traveled, which is 3t squared. Okay, so to write it in standard form, I probably wouldn't leave it that way. I'd probably write h of t equals negative 3t squared plus 200. Okay, so now just think about these graphs. Like this situation, if you have time down here and distance here, it's kind of going like this. If you have, I mean, that makes sense, right? As time goes on, it travels more distance. But this graph, if you have time here and height here, then it really starts at 200 and goes down, right? As time goes on, it decreases. Well, I guess it's not an arrow. It decreases in height. All right, so last page. So suppose the object was not dropped, but was actually thrown downward from a height of 200 feet above the surface of the moon with an initial speed of 10 feet per second. Rewrite your equation for the height of the object above the surface of the moon as a function of elapsed time t to take into account this initial speed. So I'm actually going to draw a new little table. So I have time, right, in seconds. And then I'm just going to put here, and then we have instantaneous speed, which was in feet per second. And then the next thing we had was on the interval 0 to t, what the average speed was. And then on the interval from 0 to t, the distance traveled. Okay, so 0. Now, at time 0, it's actually not 0 here because it says it has an initial speed of 10 feet per second. So actually at 0, it's 10, and the average speed from 0 to 0 is 10, and the distance, though, is 0. So it hasn't traveled at all, but it starts with this instantaneous speed of being thrown. Okay, so now let's look at our next. So at 1 second, it's actually, now remember, you have, it says that, don't forget that on the moon, the constant acceleration increased speed by 6 feet per second per second. So if I had 10 to start with, plus the 6 that's already there, this is 16. And then 0 plus 16 over 2, right, equals 13. Oops, not 13. Oh, 13. 68. And then I have, now I'm just adding 6, right? So 2, I have 16 plus 6, which is 22. And then on the average, oh, sorry, this is 10. 10 plus 16, not 0 plus 16. Because remember, it's from 0 on 0, which is 10, plus 16 over 2, which is 13. And then 16 plus 6 is 22. So on the out, now remember, at 0 it was 10. The speed was 10 plus 22 over 2 is 16. And then we're going to actually try to generalize it to just t. So t, the way that I got each of these was I had to I had the 6 applied to it, right? 6t, so 6t, plus the 10 that I started with from 0, right? That's how I got each of these. And then I had to do the average, 10 plus whatever the instantaneous speed was, which in this case is 6t plus 10, and then all of that divided by 2. So when I take, I'm running out of room here. Okay, so let's make sure that you understand where we're at. For each of these average speeds, I'm on the interval from I want the average speed at 0, the average speed at that second, and then I take the average of them. So I have 10, which is 0, plus 16 here, divided by 2, I get 13. 16 plus 6, because I got 22 here, that's my instantaneous speed at 2 seconds. So I go from 0 to 2, so 10 plus 22 divided by 2, I get 16. And then if I was going to put t in here, I would start with 10. I would add 6 times however many seconds it is. And so I, again, still want to start with 10 and find the average of 10 and 6t plus 10, which is just 3t plus 10. You can see that. 3t plus 10. It kind of went over the line. This is 3t plus 10. Okay, so now let's figure out the distances. Distance, remember, is average speed times time. So average speed, 13, times time, 13. Average speed, 16, times 2 is 32. So we're going to do the same thing with t. Time, t, times average speed, 3t plus 10, equals 3t squared plus 10t. So when it says rewrite your equation for the height of the object above the surface of the moon as a function of elapsed time t to take into account this initial speed, well, remember this is distance. I'm going to have to continue my work right here. This is distance of t, 3t squared plus 10t, right? That's my equation for distance. But it's asking me for my equation for the height. Well, it started at 250 feet, so the height, the equation for the height of at t is 250 minus the distance, just like we saw in the last one. So you could distribute that or keep it the way it is. Okay, so this is my answer to number 16 above. I just ran out of room again. Okay, so how is your work on these following object problems related to your work with the rabbit runs in the previous test? Well, we didn't do the rabbit runs because that was part of 9.1, but basically what it's asking for is, or referring to, is that they're both quadratic. So you can just not answer that. And then why are the distance fallen and height above the ground functions quadratic? Well, if we had used this table and made a first difference and then a second difference, they would both have second difference the same. And you have a linear rate of constant change. So your second differences are always the same. So we didn't do the rabbit runs, so it's a little bit hard to answer that question, but the distance fallen, you have second difference is the same. It actually has the shape of a parabola, remember, for the that we just did on the last page. And you have a constant, oh, well, we can just leave it there. Okay, so hopefully that helps you with 9.3. I just think that the table will really help. The reason that they gave you a table to figure it out is because I think the table really helps you think through what's happening with each situation. Like, you know, I'm seeing a pattern and then I extend that pattern to the t, and then that's how I get my equation. So that's why we made a table here. You know, you kind of saw what was happening with 0 time, 1 second, 2 seconds. So what would happen at t seconds? So if you just follow that through the table, then you can see a pattern and use that pattern over and over.